Hey, welcome everybody. Today is kind of a first. We're going to have two presenters back to back on the same topic on machine learning. I discovered both of them in Make magazine. They both had articles a couple 3 months ago about machine learning, and I discovered they both work for Microsoft. What I didn't know is one of them works for Microsoft in France, and the other one here locally. But Benjamin has agreed to join us very early in the morning, his time, for the second half of this meetup. I will be watching the chat room, so if you have questions, put them in chat. It's generally easier to hold things towards the end, but if you have an immediate question that you really want me to answer at the appropriate time, I will interrupt the presenter. So, but keep track of your questions and put them in chat, and we will get to them. I'm going to be muting everybody except the speaker, including myself. But I will be watching chat. So if you have questions, by all means, put them there. So. Welcome to the North City Tech Meetup. We've been doing this for a number of years. Has it been 4 years or something now, Christopher? Christopher started it, and we're going to be, 5 years already. Well, we're going to be probably moving to a more random schedule, just because I've been so busy. I haven't had time to book speakers every month. I'm going to try to get back to every month, but it'll probably be every other month for a while. Just because it is time consuming to call people and get them corralled into talking. But for this month, we've got two of them, and they're both great. We're going to start with Jen Foxbot. She is, as near as I could tell, active in absolutely everything. She has a BA in physics from Occidental and an MS in mechanical engineering. So that makes her an engineer, a maker, and she's here tonight. That makes her an educator. And so she, as near as I can tell, has at least 2 full-time jobs, one at Microsoft, one at Foxbot Industries, which is her own site. And she could perhaps tell you a bit more about that, but links were provided in the information sheet that went out. Then we'll be joined by Benjamin. I assume his last name is pronounced Cabé. I'm not sure about that. Actually, I haven't asked Jen and Benjamin, do you two know each other, or is this random?
Yeah,
okay,
we do, virtually, of course. I haven't had the pleasure of meeting him in person, but yeah, we actually have worked together previously.
Okay. Cool. And so Benjamin is located in France, does work with open source and Internet of Things. And so today's topic will be on machine learning and projects you can try at home. So pretty much a hands-on approach, not so much theoretical. And at this point, I'm just going to throw it to the wall and say, Jen, go ahead.
Woohoo! Thanks very much, Ken, for the lovely intro. As Ken mentioned, my name is Jen. My last name is Fox, but it's a hilariously common name. And so in college, I came up with the handle Jen Foxbot, and it kind of stuck. So that's kind of what I go by for all my maker projects. It was an inspiration for the company that I founded, Foxbot Industries. So that company provides an arts-based approach to STEM education. Like Ken mentioned, I have a full-time job at Microsoft, exploring ways that Microsoft can support and engage makers. That takes up most of my time, but I still am really passionate about education. And so I really enjoy opportunities to do things like this. I still do some stuff on the side. Pandemic made it really hard to do hardware workshops, which is kind of my specialty, but figuring that out as we go. Cool. So why am I here talking about machine learning? Well, I am a huge advocate of folks understanding how technology works. I see technology as a tool to add to your bag of tricks. It's also really important for us to understand how these types of things work, because let's be real, we all use the internet, and machine learning algorithms drive a lot of the content that we see on the internet. And when we start to use tools like what I'm going to show you, a tool called Lobe, when we start to use tools to play around with machine learning, it helps us to understand what it is capable of, what it's not capable of or what its limitations are, and how we actually can be better advocates for ourselves and our community members when it comes to policy. Machine learning is just a fancy term for some software. I'll kind of get into that a little bit in a second, but I just want to make it more accessible because I think a lot of the conversation is very high level, and it's something that I believe a lot of folks can actually understand the basics. And there are tools now to poke around with it where you can be like, oh, okay, this is kind of what it is. And also you can build projects with it, which is super fun. So yeah, that's kind of why I'm here. So let's start to get into the weeds. If you are interested, and I would highly recommend checking it out, you can get Lobe, which is a no-code machine learning training program. Basically, you can build your own machine learning models without writing any code. It's super fun, and it's free. So if you want to download that, I popped a link into the website, or sorry, into the chat, aka.ms/lobeai. If you put that into your browser address window, it will take you to the download site. So I'm going to share my screen, and I'm going to do some drawing because I love to draw. Okay, so what is machine learning? What do we actually mean when we say machine learning? Machine learning is kind of just a fancy way of saying science or statistics. So in science, what we do is we end up, ooh, that's hard to draw a data point. So we often take a bunch of measurements in science, right? And we get a bunch of data, and maybe the data kind of looks like this. And then we go and we say, okay, I want to look for a pattern or a trend in this data. And maybe I draw a line like that that kind of reflects the average scatter of this data. That's really what machine learning is. Although in machine learning, what we are often doing, can I move? Oh, okay. I don't know how to move around in this one. So we're just going to use a different color. So often in machine learning, what we're doing is we end up with different categories of stuff. Like maybe we have a cluster of dots over here that we label cats. And then maybe we have a cluster of dots over here that we label dogs. And we basically, quote unquote, train the machine learning algorithm to recognize this as a category and to recognize this as a category. And of course, I'm simplifying a lot here, but at the end of the day, machine learning is just math and statistics put into some code. What Lobe does is it focuses on image classification. So basically we take a set of images and we label those images for the program or the software code. And once you have enough of those images, the software code starts to get a sense of like, oh, if I get a new image, I should put it into this category, or I get a new image and I put it into this category. And the important thing to note here is that computers don't think or learn even close to the way that we do. I have a kind of a problem with the term artificial intelligence because we don't have anything close to intelligence here. For example, if I trained the program to recognize cats or dogs and I showed it a picture of a bird, the program has absolutely no knowledge of birds. And so it would shove the bird into either the cat or the dog category. Kind of based on some whatever features it had decided to label the cats and the dogs. And we can go and kind of modify those things, but the better thing to do would be to recognize, oh, okay, this program doesn't recognize birds, so I'm going to create a new set of data over here, and then I am going to tell the machine that these are birds, and then it would be able to put in a bird category. So that's basically what Lobe is doing. My specialty is hardware. So another term that you might hear thrown around is edge or embedded. And that really just means that instead of running these models on the cloud or basically just like a computer, we're running them on much smaller devices, even smaller than our phones. So we don't really include some people include our phones in embedded devices because, you know, we carry it around in our pockets. It's kind of like free to the world. We're not tethered to a desk, right? But edge devices often refer more to things like this. I have a close-up camera right here, and I'll switch to that a little bit later. So that's what I mean when I'm probably going to use this term at some point, edge devices or embedded devices. Basically, you can think about them like simple computers that do one task. For example, your router. Your router is responsible for connecting to the internet and acting as a gateway for your home Wi-Fi. So your router is a quote unquote edge device, and lots of other things are as well. I also will probably use the terms microcontroller and microprocessor. And so what are those? A microcontroller is what I just defined, a simple computer that does one specific task. So again, I'm going to pick on the router. Your router is a great example of this because it has this setup loop where it kind of initializes things, it sets parameters, it defines the things that it's working with. And then it goes through this infinite loop where it basically is kind of waiting for you to come home. And when you come home, your smartphone connects to your router, and your router connects you to the broader internet, the World Wide Web, as we say. And sometimes microcontrollers get a little messed up in that infinite loop. And so what do you do when it's broken? You unplug it and you plug it back in. And for a long time, I was like, why the heck does this work? That doesn't make any sense. And the reason why it works is because the structure of a microcontroller is that it has that setup loop, and then it goes into this infinite loop where it just keeps doing the same thing over and over. Sometimes it can mess up stuff in that loop. And so when you unplug it, you basically force it to go back through that setup loop where it'll like correct anything that might have gone awry in that infinite loop. So that's why that actually works. It's not magic. It's actually code that helps it reset, basically. The difference between a microcontroller and a microprocessor is that a microprocessor is really more of what we think of as a computer. It can do multiple things, not exactly simultaneously, but more so than a microcontroller can. A microprocessor, you can kind of think more of like as the computer's brain. Where a microprocessor tends to communicate and send instructions to many different microcontrollers. So if you were to open up your computer and look at that big green board or the motherboard in there, there would be a central processing unit, which would be the microprocessor, this black chip with a bunch of little silver legs on it. And that would be connected to a number of different microcontrollers. It might also be connected to different microprocessors for things like memory and stuff like that. But basically that microprocessor is acting as this manager who is instructing the microcontrollers to do many different things. So your computer can run video and sound and store memory and have 3 million different tabs open on the internet all at once, and it can handle all of those things. Okay, cool. Does anyone have any questions? I also forgot to mention, this is casual. Please feel free to type questions in the chat or just like raise your hand or whatever. Ooh, is there? Okay, so far so good.
So good. Right. This is a pretty technical crowd in general, so
great.
Yeah, I think we can. It's good so far. Keep it going.
Okay, cool. So now what I'm going to show you is the Lobe website. Cool. So we're gonna do the dangerous one, and we're just gonna share the whole screen. Okay, so this is the Lobe website where you can go download it. Maybe it's gonna load, maybe it's not. Yay, hello. There we go. So you download it. It's still an early program, so I'm pretty sure that they still ask you to submit your email. It's not to sell your data or anything like that. It's really just to kind of keep track of like how many people are downloading, so that they can get a sense of like what's working, what's not working, and make it the best possible platform for people to use. So I'm going to show you, now we're going to dig into building a simple project. Okay, so can everyone see the Lobe, the actual like Lobe program that I just opened? You should see an untitled thing and then a trash classifier project, which has a Ghirardelli wrapper in it. Cool.
Yes, that's showing up.
Awesome, thank you. So we're going to look at how to make a new project. All right, and computer is running slow. Okay, so the first thing we want to do is label our project something that makes sense. So I'm going to call this trash class 2, so I don't get confused with the other one. And really what you start to do now is you just import data. And there's a number of ways to do that. One of them, kind of maybe the easiest or the quickest, is to just take pictures with your camera, which I don't think is going to work at the moment because I'm in Zoom. Oh, okay, that's cool. It's going to snag my other camera. So what I would do, I'm going to move this for now. So what I'm going to do is I'm going to put like a trash item in there, and I am going to say this is garbage. I'm going to take a picture. Click, take photo. And I'm going to rotate it. I'm going to take some more photos. The sound effects are really satisfying. I'm going to rotate it more. Okay, I took 8 pictures of this one thing. What other trash do I have? I'm kind of one of those people that I don't put the glue on my Post-its in the garbage. So now I'm going to take a picture of the glue on the Post-it. This is actually probably going to be very confusing for my model, but that's okay. We'll see how it works. I did not plan ahead and get enough trash. Okay, so I'm just gonna we're gonna make do with what's on my desk. I'm gonna take some more photos of garbage. And you kind of want to move it around the frame. Maybe, oh, I already did flip it. Maybe I want to hold it so I can get some pictures with my hand in the frame. Okay. And so you start to see this category filling up here. But right now, my model is not doing anything super interesting. It's kind of just got one category. So like I mentioned before, the machine learning algorithm doesn't really quote unquote know anything at this point, because if you only have one label, it's kind of meaningless. So now I'm going to make a new label, which you just do by clicking on it. I'll call it recycle, and I'm going to take some more pictures. Again, just kind of move it around. And the other thing that I might want to do is change the lighting, or maybe bring it closer to the camera, farther away. And I kind of am constrained with the vision of my camera at the moment. And then maybe I'll take a picture. It's going to really confuse my model. I'm going to take a picture of the paper part of my Post-it. And then maybe I will get some cardboard. Cardboard box here. Oh, except that's white. I don't want a white box. I want something like this. Okay. And so now as we look at these little bars, now it's kind of starting to get a little bit interesting, because we have something to compare to. Okay. To be full disclosure, this does take a lot of computer resources. So I apologize if my audio is a little funky. And the last one that I would do is not trash, or basically like the NA category. Maybe that's what I want to do, where I take a picture of just the table. And again, the reason why we want to do that. Ooh, does anyone want to guess why we want to do this? What happens if we don't have an NA category? Any guesses? If I didn't put a NA or a not trash category, what do you think might happen?
It's going to force something into some category or other, whether it makes sense or not.
Yep, exactly. And so in this one, I might also want to actually take some photos of just my hand. This is something that I discovered when I was building the original trash classifier project. I discovered that if my hand was in a certain position in the camera frame or the image, the model basically had learned that, oh, that hand position means this category, but actually it didn't. It would just happen to be the way that I was holding a battery or what have you.
Jen,
So,
can you please clarify, is this a model that you've already built and you're now training, or is it building the model as you go?
it's building the model as we go. So you can see over here on the left-hand side, right now I'm in the label section, and it is actively training. So if I go to that, it's going to be really slow at the moment because I'm running Zoom and all of these other things. I actually can maybe close that. That might help a little bit. So you can see, maybe if I scroll down, no, I think it's still training, but it trains as you go. And so this little circle indicates how much progress has been made. And once you have a model that has trained enough images, so you can see these red bars basically indicate that it hasn't finished training in any of the categories. But the idea is that, yeah, you get to build a model and train it and test it in real time, which is really incredible. The other thing that you can do is import data. And so one of the things that I ran into is there are thousands of different types of trash. And I started by taking pictures for about a month, not, on a set schedule, but just kind of casually when I could remember. If I went to go throw something away, either in the garbage, recycling, or compost, I would first take a picture of myself holding that object, and I would kind of rotate my hand and take maybe 10 to 15 pictures at different angles, different distances. I would try to block out the light in different ways. And then add that to my data set. And then after a month, I was like, I literally, even if I do this for another 3 months, there are still going to be trash items that I just haven't gone through yet. For example, during Christmas, like we have lots of wrapping paper. So I'm not going to get any wrapping paper unless it's, seasonally related, or I happen to have a friend's birthday party. And so what I ended up doing is I looked for data sets. And what's really nice about that is that someone else can do the work to label your data, and you can import that into Lobe. And so the key thing here is that whatever category whatever folder the photos are labeled is what Lobe will import it as. And if it is different than your existing category, it's going to make a new label. Oh, I guess you can label manually now. That's a new feature. That's cool. So you want to make sure that it is the same as what you have labeled it. Otherwise, you're going to have to go through and select them all and relabel them, which you can do. You can highlight all of these and say, just kidding, I want to relabel this as something different. But as far as I know, you can't select. Oh, you can select all. Oh, very nice. Another new feature. Nice job. Okay.
And we have a question, which I was also thinking, is the training happening on your PC or in the cloud? So where's all the thinking being done right now?
This is all happening on my computer. This is an all local program. So a lot of people have, I don't know if folks are familiar with some of the different Microsoft tools, but Microsoft also has a program called Custom Vision, which does image classification and also object detection. So that one runs in the cloud, and you're using, if you build a big enough model, it may end up costing a little bit of money. I've poked around with it and I've built some pretty big models and I've never spent more than $3. But this one runs entirely locally on your computer, hence why it makes things a little bit slow. But if you're concerned about privacy, or if you don't want to pay for hosting, you can go with this option. But custom vision is fairly similar. I think that this interface is a bit easier, is a bit more beginner friendly. So it's great for like an EDU setting, for example. It's a great question. So now this is the imported data set. And so this is really convenient because this person was kind enough to go through and label all of these different things as garbage. Now this one is interesting because I see this apple core and I'm like, hey, wait a second, I have a new Seattle compost. And so what I would want to do is create a new category with compost and move this one into the compost category. I also probably could move the paper towels into the compost category as well. But one of the tricky things about trash image classification models, or even object detection models, is that every city is different. There's a tool. I live in the city of Seattle proper, and so I was actually talking to my mom about this, who lives in Shoreline, and her recycling guidelines are slightly different than mine. And so that was one of the interesting things I discovered when I was doing this, is like, oh, every city is different, and so my data set may not extend to everybody. And that's actually kind of where, when we're talking about applying machine learning and using it to do practical things in the real world, we actually may want to use smaller data sets that maybe, aren't extendable in the ways that data sets trained on millions of images are, but they're hyper local and they're more accurate to our local systems. And with tools like Lobe or custom vision, or what Benjamin will show you, Edge Impulse, it's getting way easier for folks who are not data scientists to train machine learning models and deploy them. Okay, so the last thing that I want to cover is how do you actually get this onto an edge device? So my goal was to basically, one of the things that I would run into whenever I would go out and about and generate waste at a restaurant, or for example, at the Microsoft cafes, sometimes I just wasn't sure, is this compostable? Is this recyclable? I just want someone or something to tell me where to put it. So I called it affectionately, where does it go? So I created this little cardboard enclosure that I reharvested the electronics, which is kind of typical. But I created this little enclosure so that I press the button, there's a camera right in here, it takes a picture, and then it does inferencing on the device, or basically it takes that model and then runs the photo through the model, and the model kind of like labels it, or does inferencing is kind of what we call it in machine learning. And then it lights up a different colored light depending on what that machine learning label was. So I also had a category for hazardous waste, because another thing that was really surprising to me is that we can actually put AA batteries and smaller batteries in the garbage in Seattle, but not in LA where I lived. And that was something that I learned and I needed help with a little bit. So how do we actually get it onto a Raspberry Pi device or another type of embedded device? Well, go to the export setting. Yeah.
Before you jump onto that, there's one last question on the training. When is it complete? Does it have to go to 100%, or is it complete when you decide it's complete? Great question. So training is quote unquote done when training is done, when it has basically run all of the images that you have through the model. Now, is it done? Like, is it accurate done? Well, that's what you kind of have to test out. So that's where, when you go to the use category, you can check things. So let's see if it will do it live.
It might be really slow, but this is one of my favorite features, because let's say like, okay, I think I have enough photos, it's done training, but it's kind of unclear if the model will actually label a new image correctly, especially because I don't have a lot of images here. It's kind of looking like it doesn't want to do it. It might be, oh, there we go. Okay, haha, just is taking its sweet time. Whoops, oh, come back. So in the use category, you basically can help, yay! You can help retrain the model. And so then I would check this one and see what the label is down here. And it's looking like it's going to be garbage. Oh, okay, it's just going really slow. Okay, so it is recycling. If it did get it wrong, I would click this button and then you can relabel it. But for now, I'm like, yes. And then you actually, by testing your data set, you can add more images to your model to make it more accurate. And then let's just test the not applicable category, where it's just the desk. Yeah, cool. So to export, you can go, oh yeah, it's real slow. Okay, thank you for your patience. So I prefer TensorFlow. This is a nice kind of option. There's a lot of sample code that you can use where you basically just kind of take the TensorFlow model and shove it into the sample code and change the label outputs to match whatever you have over here. But you don't really have to be a code. You have to know how to read code, but you don't have to know how to write code necessarily. So you just pick where you want to save it. I'm not going to do it right now. Nope, cancel please. So oops, no, we don't want that. I was going to show you, stop training. So this is the one where I imported the whole big data set from Kaggle, which is, I believe, a Google-owned website, but they have data sets on all sorts of things. That actually might just be too much for the computer to handle. So this one has thousands of images. The trash classifier that I ultimately deployed on my Pi for my trash classifier project, I had, I think, 5,000 photos, and I was on a different laptop, and my laptop was like getting really, really hot. So it's not the most efficient method. When you start to get into bigger data sets, that's when you want to start thinking about going to the cloud, which is basically just like, I'm going to borrow other people's computers that are specifically designed for these types of things. But this one is still training. And what is really cool down here is you can see 93% of your images are predicted correctly, 7 incorrectly. I also really like that you can kind of see these bars kind of help you compare. So the recycle category has a lot. So what I should do is I should go through and add way more photos in the garbage category until it fills up to where the recycle category is. So I'm going to exit this. We're going to stop training so my computer will move a little bit faster. And what I'm going to show you now is how we are deploying a prediction on the Pi. So, hello, please. Uh-oh. Oh, shoot. Did it get unplugged? Okay, maybe we'll show it. Live demo. That's a fun game, isn't it? So maybe not. What I can do though, oh, okay, yep, we're just gonna log in again. Maybe we're gonna log in again.
So just to be clear, you're now logging into your Raspberry Pi at the command line level.
Yes, exactly. And while, computer is still going really slow. And it froze. Oh, connection timed out. Did I get a different IP? Okay, what I will show you really quick, if I can, because this, I always forget that this is gets in the way. Okay, we're gonna move this down here. So my team put together a bunch of sample code. So the kit that I'm going to show you is this Adafruit kit here. And there are a bunch of learning guides. So this is like the getting started guide. This is the inferencing that I'm going to try to show you. And then this one is kind of a more like, how do you build a model and do continuous learning, which is basically like taking models or taking photos on the Raspberry Pi, sending it back to your computer, and then importing them to Lobe to update your model as you go. And now I realized the reason why it's not working is because I unplugged it. That's really funny. I've been doing hardware for about 10 years, and honestly, power is still probably the most common problem. Well, that's good. Okay, we're gonna try this again. So this is the GitHub repo where folks can go, and if you click the code button and you copy this, you can download it, or you can download the zip file. And so this is a really cool program because it will help you. You can kind of use this as a wrapper for whatever Lobe model you have. So basically, what you want to do is just put your TensorFlow model onto the Pi, and then into a folder titled model. And if you need instructions, there are instructions on the Adafruit site and on the GitHub site, and I will share those links in a second. There we go. Okay, cool. See.
Okay, you just threw out the word TensorFlow, so you might want to mention what that is.
Yes, thank you. So TensorFlow is a software development package, basically, that is specifically designed to do machine learning on edge devices. So the whole software package, you can go from the ground up if you want. That said, you kind of like training a model in TensorFlow is a huge pain. I was talking with the founder of Adafruit at one point, and she was really stoked on Lobe because before Lobe, you had to only use code to train the TensorFlow model, and it was really difficult to do something that was not trivial. Like, for example, the default example training project for TensorFlow is a sine wave. So you use some math to generate a sine wave to train the model, and then the model learns what the sine wave looks like, and then it makes its own, which is a little bit fuzzier than the actual math generated sine wave. And that's not super, like, it's cool, like, and it's really impressive that you can get that to run on a Pi, but it's, not maybe fun exactly. And so what was really cool about Lobe is that you can train a model and export in TensorFlow, and then kind of use the other parts of the software package to run the model or to deploy the model and get some prediction. Is that helpful? I'm trying not to get too much into the weeds.
Right. So it sounds like what's happening is you're using Lobe to create the model, which it then outputs in Python, or which is then fed into TensorFlow to actually execute.
Yeah.
I'm not quite sure if I have the Python part right though, where the model is and how the Python comes into play. Whether So
it does have support for other languages. I'm most familiar with Python because that's what I use for the Pi. But yeah, I want to say there's support for C++ as well. Don't quote me on that, though.
Is the model in Python, or are you just calling the model from Python or C or what have you?
Oh, that's a really good question. So basically what happens when you export a machine learning model is that you end up with there's kind of a bunch of different pieces, and it's been a hot second since I have poked around with them in the weeds, but basically you end up with so like I mentioned earlier, machine learning is really just statistics, and you end up with these like kind of intense equations, and each of the variables in the equation has an associated parameter for it. Basically, we call them weights, because like if it has I'm probably I am simplifying here, but like if it's a bigger number, that parameter gets more weight to it. It affects the output more. So let's say, for example, in my images, in the garbage category, it might be using size of the object. So this is smaller than this. And so like, again, like simplifying, like if the image says like size of this color matters, then in the garbage category, size gets less weight. And in the recycling category, larger size gets more weight, or sorry, size gets more weight. So if it's bigger, it matters more. So what you end up doing is you export basically this like really, really long file of numbers, and then those numbers get applied to an equation. And so TensorFlow basically handles all of that messy kind of difficult math, and you can kind of just deal with the layer above that. Is that helpful?
That's very good. That's actually one of the best explanations I've heard. Thank you.
Okay, I'm really happy to hear that. It look very hand wavy, but I'm really happy to hear that.
It's confusing stuff.
Yeah, and it's interesting because I'm not even talking about neural networks, which it's kind of the same concept. Like we're using equations. It's a lot of linear algebra. It was kind of funny switching from physics to engineering. Like you kind of use all the same tools, like a lot of linear algebra. I was joking because like there was a point at which I took a class, and it was like the 14th time I learned about eigenvalues and eigenvectors, which are basically linear algebra terms. And then I go to and learn machine learning, and I'm like, oh, it's the same stuff. I can't get away from it. Apparently very useful. So TensorFlow helps to do that. It also like kind of reduced the size of these files, so it could actually run on these smaller devices. And then the cool thing is like, yeah, you can use multiple different languages on top of the TensorFlow platform. So if y'all can see the desktop camera, so right now it's running a simple prediction. And if you wanted to just change the output, you could go in here and say, well, yeah, so I think, yeah, it's calling the labels from the model. So as long as you put your model, I think there's 2 files that get exported from Lobe, and you just put them in the same folder, and then you can do kind of a live test of your model. So this is a different one than I was showing you. We just did a rock, paper, scissors one. So what's interesting is that it's looking at the ceiling and calling it scissors. It's not scissors. It's fine. Let's see if I can get it to paper. Nope, that's rock. So one of the things that's really interesting is the model, like I said, is not smart. And if you train it on a different camera with a different background, it can get really confused. And so my advice is to take pictures, like if you're going to deploy it on a Pi, take pictures with the Pi camera in the view that you're going to use it, and then import that into Lobe and train your model, and that will make it the most accurate as possible. But in this program, you can kind of see like how accurate it thinks it's doing, how good it thinks it's doing. Oh my gosh, I'm at 7:46. Whoopsies. It's supposed to go for 30 minutes and I just talked forever. Cool. So, all right. I'm gonna switch my camera. I'll turn my Pi off. And if Benjamin's here, I like to say his name in French, Benjamin. If he's here, he's welcome to take over. And if not, I'm happy to field questions.
Oops. Yeah, I don't see him here yet. So it sounds like what you did was you took you used Lobe to build a model of garbage and recycling by providing a certain number of pictures. some of which you took, some of which you imported from a database of pictures. Then you executed the model on Lobe on your PC, proved that it worked, copied it, the secret magic numbers of the model onto Lobe, now running on your Raspberry Pi, which would then look at pictures directly from the camera. Is
Yep.
as someone who does some image processing, is it, are you snapping a picture each time, or is it pulling it out of a video stream on the Pi?
Yeah, technically it's so it looks like a video stream, but it's basically technically taking a picture.
So you're going snap, 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 and then whenever it finds something in the field, it says, aha, I'll run the model against that.
Yeah, so it's like it's capturing a single frame as you go, and it's doing that very, very quickly, which is, again, really impressive.
Is it? Yeah. So how fast? So you did the training, which took some time, but now it's actually running the model against these frames. So how fast does it actually do a classification of a particular image? Is that sub-second, sub-frame? Is that frame speed?
That's a good question. So so when I was doing mine, I was taking pictures like those like photo booths. Like you push the thing and then you wait and you're like, so the Pi camera takes about 2 seconds to warm up. And so I would take the picture and it would kind of like blink the status light. So I would have to wait for 2 seconds. The camera stream was actually our team's clever way of getting around that. So it still takes 2 seconds to warm the camera up, but then you kind of just like keep it on. So inferencing, it kind of is, it's going to depend on some factors. The Pi is not going to be nearly as fast as a computer, a laptop, or even your smartphone, just because, you know, it's a much smaller device. It's much less powerful. But you can get an inference within a second. And if you use an accelerator, so there is hardware that is specifically designed for ML, machine learning. The Jetson Nano, I believe, is one of them. You have the Google that you can actually plug into the Raspberry Pi. You can plug it into the USB ports, and it will basically do the inferencing on the stick so that you can use the Pi for its wonderful hardware capabilities, but it will speed it up. And so that's what you would want to do.
Oh, you're slowing down there. You use your computer doing something?
Like Pi wouldn't be fast. Oh,
yeah. You seem to be frozen there, Jen, unless it's just me. Anyone else seeing?
Yeah, no, I can confirm. She's dropping out just a little tiny bit.
Yeah, with a very odd picture on the screen. You wouldn't want to see it, Jen. All right. Jen, if you can hear me, make a noise. Okay. Looks like, okay, so I know Maurice, you haven't. Whoop.
I can hear you. Maybe if I stop video.
Yeah,
Is that better?
are you running a model on your PC as well?
Is that better?
I can hear you. Your video is still frozen.
Sound has improved a little bit.
Yeah.
But now she's gone.
Jen, are you there at all? Maurice, I know you have a question. When you get Jen back, we'll get that one answered because I have a similar question. And Benjamin has not yet shown up.
My computer.
Jen, you want to try coming in on your phone, maybe?
Oh, I do not have Zoom on my phone.
Okay.
Let me try.
You are
yes. Back. I was joking that my computer, I'm on my work computer because technically this is work related. Maybe I got upset that I was on Zoom and not Teams.
It says your network
Quite
bandwidth is
yes.
low. um,
Yeah.
try to not,
Yeah, I've
is
been
your
fighting
video
with
off?
Comcast.
If you're,
Yeah, I turned it off because it
okay.
might help.
Okay, yeah. So it seems that you can hear us. So the question I had is, can I upload CRM data into Lobe to classify data? Let me generalize that. Is Lobe photo only, or will it take? Can you train it on other kinds of data?
Yes, that is a great question. And I was trying to answer that when Zoom crashed. So it is image classification only.
Okay.
So not even they're working on supporting object detection. So image classification is classifying an entire image. Object detection is classifying objects within that image. So you could, for example, detect multiple different things within an image. That is very energy intensive. So I think that they're trying to find creative ways to do that locally without, destroying your computer or burning up your computer. But that said, people have done some really creative things in Lobe. So for example, there was someone who was doing audio analysis, and they trained Lobe to identify different instrument sounds by taking pictures of audio samples from different instruments.
I like that.
So if you could somehow take images of CRM data, theoretically, yeah, you could totally train an ML model to classify CRM data.
Okay, and but I presume there are other publicly available systems like this where you can feed in other kinds of data without necessarily going to Google or Azure or something.
Yes,
but Lobe itself is focused on images.
Yes, it's also Lobe is the only all local machine learning training program. I am gonna call out Edge Impulse. So they just had a conference last week, and Edge Impulse is a cloud-based platform, so it runs in your browser to train custom ML models for edge devices. And they've made, it's not quite as simple as Lobe, but it's close. And that one you can do all sorts of things. So you could take accelerometer data and use that to train a model. You could take audio files and do like keyword detection. Theoretically, you could probably figure out how to do CRM data. That would be really interesting, and I would love to see if that's possible.
Cool. Yeah. So there are an awful lot of resources available for playing around with machine learning. In this particular case, we're looking at a simple way of doing training and then moving the model onto an embedded controller or microprocessor, in this case, the Raspberry Pi. And that's the beauty really of Lobe, is how easy it is to build this standalone device like your image, your garbage classifier.
Yeah, exactly.
Now, talking about training it, in general, you hear the more the more data you feed it that's classified already, the better you'll get. Does Lobe have practical limitations in terms of what you can practically train on a PC and then practically execute on the smaller microcontroller?
Yeah, that's a great question. So the feasibility limits really have to do with the number of images. So if you're doing a fairly simple image classification data set where you have a few different options, and your labels do not require more than a few hundred photos, you need a minimum of like 10 photos in a label for it to be reasonably accurate. But when you start to get into, like I was mentioning, like my garbage data set and my recycling and compost data sets needed thousands of photos just because of the vast number of types of objects. And that really started to slow down my computer. It got to a point where I was like, oh, I can't add any more images. And that's really a limitation of my local device. That's a limitation of my computer. So what's pretty cool though is that we're only doing inferencing on the Pi. We're not doing any training. And so regardless of the size of your image data set, that is what tweaks those model parameters. So those numbers that get exported, the size of those files don't really change. It will change, let's say if you used Edge Impulse to do embedded speech, you would end up, so image models have the largest number of parameters, embedded speech kind of is below that. And then if you use sensor data, you can get models the size of kilobytes. So you could shove that onto a much, much smaller device, like an Arduino Nano or something like that.
Great. So Benjamin has joined us. Jen, I'm not sure if you'll be sticking around or not, but I hope you will, because perhaps there'll be more questions as we go. But at this point, any last questions for Jen before we switch on to the second part of our presentation? We have some thank yous. Yeah, thumbs up, some thank yous. I thought it was great. You know, I tried to follow this stuff, but some of that was some of the best straightforward explanation I've heard. So I really appreciate that.
Thank you so much. Great questions. I love the questions. It was really, really fun. Thank you for the opportunity.
And whether or not you like it, people know how to get a hold of you. But it's
yeah, please do.
Further questions. So I'm going to turn this over, and Benjamin, I'm not going to pretend to pronounce your name with the proper accent, but Benjamin Cabé, who is also with Microsoft, currently located in France, does a lot of work with machine learning and Internet of Things. And we just heard Jen do a good introduction to Lobe and show how you could input images, train them, and then transfer it over to Raspberry Pi to actually execute the training model. So at this point, without further ado, I'm going to turn it over to you.
Thanks for having me. It's a bit early for me, but it's going to be an interesting presentation, I hope. I'm sorry that I missed Jen's part, so hopefully there won't be too much repetitions, but I mean, we're actually going to talk about sensor data, right? And machine learning for sensor data and those kilobytes large kind of models. This is exactly what we're going to cover. We're going to talk a bit about Edge Impulse in terms of, specifically in terms of tooling. But yeah, the story that I want to talk about today, or the experience that I want to share, is mine. The experience I had building an artificial nose. So that's for the teaser, and that's for the, I guess, the second part of the teaser. That's the artificial nose in action, and I want to tell you a bit about why I built this and how it works. So it's a device that effectively uses off-the-shelf hardware, really cheap hardware, actually. And we're going to talk a bit about the numbers and what you can expect and how far you can get with literally just a few dollars worth of embedded microcontrollers and a few dollars worth of silicon, essentially. But yeah, the device can smell and recognize coffee, whiskey, make the difference between whiskey and vodka, potentially, and all of that with reasonably low-cost sensors. And so, yeah, so why did I build that, and how does that work? So I'm Benjamin, however you want to pronounce it, Cabé. I'm a program manager at Microsoft. I'm part of the Azure IoT, Azure Internet of Things product team. And while I guess my colleagues, my peers, other program managers on the team actually work on shipping features for the Azure IoT cloud platform, I'm more on the community side of things. And I guess I'm almost more of a software engineer than I am a product or a program manager. And I try and be the interface with some of the third-party communities out there in terms of machine learning, AI, open hardware, open source software, and making sure that folks who are happy and excited about whatever is their tool of choice, which doesn't have to be Microsoft in any way, making sure that they have a great experience when they want to connect their solutions to the Azure IoT cloud, right? And so, in case you didn't figure, but I think it was mentioned in the introduction, I'm French, and I do like bread. I do like actually making my own bread. And what I mean by that is that for the past couple decades, probably, I've been trying to perfect my bread recipe. And when the pandemic hit, early in the pandemic, I guess like many people, I was stuck at home and I had time on my hands to perfect my bread recipe. And I realized that maybe I could use technology to help me realize when my and figure out when my sourdough starter would be perfectly ripe. So that was the ideas of the sort of the itch that I needed to scratch, right? You may have heard about this in technology and in open source specifically. Usually you don't like build something just for the sake of building something. You scratch your own itch, right? And that was mine. And at the same time, and it might be relevant for the rest of the discussion, at the same time, that was the situation of on the shelves, right, in the supermarkets, hardly any flour. So buying bread was a challenge. Making bread was a challenge to some extent early in the pandemic. But in any case, what I wanted to do is figure out if I could build some kind of device that would, essentially smell my sourdough and give me some indications about whether it's the right time to actually bake the bread. And I knew of some solutions out there. This one, I think the website is still around, sour.io. It's based on an Arduino and a bunch of sensors. It gives some feedback on the condition of the sourdough, but it's not necessarily smart. It is, if I remember correctly, it has a temperature and the humidity sensor, which kind of makes sense, I guess, for monitoring fermentation. And it has an ultrasonic sensor, a sonar, essentially in the lid, which allows to measure the rise of the sourdough, which is also great and something that you likely want to do to figure out when it's perfectly fermented and at its highest amount of fermentation. And then I think the device sends an SMS when a particular threshold is met. But that wasn't really smart enough for me, in that the science, I guess, of bread, it's much more than just monitoring the humidity and the rise of the dough, right? Because depending on the time of the day, depending on the ambient temperature, depending on the atmospheric pressure, you name it, there's tons of parameters that one day a super high sourdough will be great indeed, and one day it will be almost the opposite of what you want, right? So I wanted to build something smarter, I guess. And this is where maybe I should do the disclaimer. So yes, it's going to be a TinyML, and one way or the other, I'm sure Jen introduced TinyML to you all. It's going to be a TinyML application, but interestingly, I've been, I guess, in the software industry for 15 plus years. I'm pretty comfortable with a wide variety of programming languages and embedded development, front-end development, you name it. But machine learning, for some reason, is something that eluded me, like neural networks, the maths behind it. Even if I tried to look at maybe a Hello World kind of sample applications, here is how you're going to train a model to recognize single-digit bitmaps. See, it's easy. It's only 20 by 20 pixels, and here's how you would proceed. I would just not click in any way and just not get it. So this itch that I wanted to scratch was, not only trying to see if I could build a smart device to help me bake better bread, but it was also trying to see if I could finally get my head around machine learning. And I sort of already had the intuition that having something more tangible than pixels in the form of like sourdough would maybe help, and it did, but it actually helped way more than that, because I think at the end of the day, it helped me make more people realize that machine learning might be applicable to more scenarios than what they might thought. And if they also felt stupid by not understanding neural networks and all that stuff, then, I mean, they probably were not alone in that situation. So yes, TinyML is this idea of running a neural network and like taking data, running it through a neural network and an AI model on a super small piece of silicon, essentially, right? And so something that not only doesn't cost much money-wise, but also something that doesn't cost much in terms of energy, right? Running, making a prediction in terms of, yes, the sourdough is great or it's not so great. Something that really, yeah, a kind of device that could run on batteries for years, literally. That's the kind of use case and target. And so I knew very little about AI, or at least any time I would have tried to build my own AI application or go through some kind of tutorial, I got stuck real quick. But what I knew, though, is that my idea of trying to build a device that would smell as a sourdough starter would still be like a typical AI solution. Although I didn't know exactly all the steps, I knew what those steps were, right? One is acquiring some kind of data set to train the model, having some kind of hardware to acquire the data and to run the inference, right? For good old machine learning applications, this would be probably some kind of GPU. For an embedded application, it would be more a microcontroller kind of device plus sensors. And then I would need to build a model, and I would need some kind of software framework, software pipeline to support my use case. And so assembling the data set, I kind of knew what I wanted to do. Like the idea would be smelling, acquiring the smell, and we will see how that works to actually smell things with electronics, because that's actually interesting as well. Because and I think you have kittens behind me, so if you want some fun distractions, you can try and they are like 8 weeks old, so they are a bit. It's 5 a.m. so they're like, why did you wake us up? Where was I? Yeah, data set, like smelling. Kind of a quick note on that. Like when we think embedded sensors, I think many of us, we are fairly familiar with thermostats, with monitoring humidity, temperature. There's tons of sensors out there. And the fact that there are gas sensors for detecting and smelling things like ammonia, ozone, ethyl alcohol, etc. I think like we don't necessarily think about it. And when you start thinking, oh yeah, whatever physical thing I want to measure, there's probably a sensor for that. And even before thinking AI, it's yeah, that's interesting to keep in mind, right? So the data set, I wanted to smell my sourdough starter and then bake some bread and then like use that as my my data. This smell gave me a bread with that I would say is 8 out of 10 in terms of crispiness and being really shiny, really golden brown and things like that. So that was the data set, but there's a caveat, hence the emoji there. The hardware, I knew what I wanted to use. Like I actually knew there were gas sensors for smelling / detecting things like ethyl alcohol, carbon monoxide, volatile organic compounds. So I was set on that front. The model, like the architecture, the mathematical model of my future neural network. This is where I was really, like literally scared and didn't know where to start, but more on that later. And then the framework, I kind of knew that I wanted to use. So TinyML, although TinyML in itself is not necessarily a framework, it's more the generic term for doing ML on small devices, but the framework would likely be TensorFlow Lite for microcontrollers. But yeah, I mean, I knew a bit where I wanted to start, but some areas were not as clear as others. In terms of the data set, like I started to mention, this idea of building a device to smell sourdough was probably a good idea, except that if you remember the flour situation on in the supermarkets, this would be a challenge to build a model where I correlate a particular olfactory fingerprint, I would say, of the sourdough starter to the quality of the baguette you would get when using it, because it would require baking dozens and dozens of loaves of bread, and I just couldn't do that. So instead, I realized that maybe I could start by just smelling virtually anything, right, and trying to see whether I could train and teach the model to recognize just that. And then something else was this challenge of acquiring data coming from a constrained device. So if I am to smell coffee or whiskey for a couple minutes to sort of capture the olfactory fingerprint, whatever that is, and we will see what it is, I would have a challenge moving the data around, right? Like converting data coming from my electronic sensors into like actual bits and bytes, and then taking these data into my training pipeline to sort of build my machine learning model. This would require me to implement some kind of, I don't know, like storing the data on an SD card on the device, and then acquiring the data by pressing a button, and then taking the SD card, putting it on my laptop, and then uploading it to the cloud. I mean, the workflow would be a bit cumbersome potentially. So this is why I ended up using Edge Impulse, which was pretty much the new kid on the block back in May of last year. They've made tremendous amount of progress since then, but it was already really good in terms of providing essentially all the tools to support people in training, like in acquiring data, labeling data, right? This is like this is 2 minutes of coffee, this is 2 minutes of whiskey, kind of stuff, like helping with a nice user interface and a nice set of wizards, almost like as in guiding you towards creating a model. Even if you don't know what an AI model is, with Edge Impulse, you get guided, and once you're done, and once you're trained the model, at least that was true for me, you actually understand what the model was. And it's not the other way around, right? When you have this example, like I said, of trying to classify single digits, the workflow, whatever tutorial you follow is, oh yeah, you want to classify single digit bitmaps, build the model that way, and then it'll work. No, I want it to be almost the other way around, right? Show me the result, and then hopefully I will understand how it works. And that's what Edge Impulse provides. And we'll dive a bit deeper into the model that I ended up building. And as Jen actually hinted at, the model is really not that complex, because it's not that complex to take fairly basic sensor data like gas sensor data or temperature sensor data and extract information and find correlations in the data and find patterns thanks to AI. A few words about the hardware I used. Like I said, it's off-the-shelf hardware and it's reasonably cheap. A few words about the specs. The brain, I guess, of the nose is a weird terminal from Seed Studio. So think of it as an Arduino on steroids. It can be battery powered. It has an LCD display, tons of interfaces to actually plug and connect sensors, which in my case, the sensors would be a 4-in-1 gas sensor, what you see on the right-hand side. It's a so-called multi-channel gas sensor, and the 4 metallic squares are sensors for carbon monoxide, ethyl alcohol, nitrogen dioxide, and VOCs, volatile organic compounds. which is like for food items is actually an interesting one to have because it helps identify the fact that it's something that actually smells, right? And has some volatile organic compounds in it. A few more words about the brain. I think we have a pretty diverse crowd today, so it's not about. I don't want to have like too much technical details, but let's just say that it is a reasonably constrained device. It's not like tiny, but it's not like you have gigabytes of RAM and gigabytes of storage either, right? Quite the opposite. You have on this particular device 0.5 megabyte of storage to store your data, to store your computer program, and you have about 200 kilobytes of RAM to actually like run the application. It's an ARM microcontroller, and it's cheap, like I said. The microcontroller with the sort of developer kit form factor, that is the Wio terminal, almost like the finished product. It's about $30. I think it's closer to $40 these days due to the silicon situation. Yes, things can. It keeps going up, unfortunately, but yeah, that's the so almost the finished product. And that's what I used because that was super convenient. You have like connectors for the sensors. If I were to create and to productize and have a more industrialized version of the nose, chances are I would be sort of building my own PCB, my own enclosure, etc. I would look at just buying the chip, right? The microcontroller itself, which, and again, this is plus or minus maybe a couple dollars these days, but if you buy it in bulk, it's reasonably cheap. It can something that I want to also mention and will mention and double click on later is that I had no idea when I started, but one thing that's interesting is that it's almost overkill. Like this device, it's small. Like it doesn't have a lot of storage. It doesn't have a lot of processing power in a sense, and yet it's probably 10 times, almost 100 times more expensive, more powerful than it needs to. If I were to really just want to tackle the issue of having a sniffing device, right? I can. Yeah, like effectively the nose, 99% of the time, it's not doing anything. The computer is just waiting for data, for sensor data, but it's not running AI. It's not doing anything really. So I could probably cut the price in like by 4 or 10 even by just trying to look at a chip that is slightly less capable, but that would still be plenty for my particular use case. So I think that's an important thing to consider. And now you might be wondering, how can a machine smell anyways? And I think that's interesting to spend a few minutes on that. Just again, like I mentioned before, just for the sake of yes, there's tons of sensors out there, and we don't realize that it's much more than temperature and humidity. There's sensors for virtually anything, and they're cheap and they're super tiny. And for when it comes to gas sensors, the way it works, and I'm by no means an electrochemist, but it's an electrochemical reaction. The idea is that on this tiny square, you have a piece of metal oxide semiconductor, which effectively is heated and is like put under a particular voltage, and then it heats up, and then it reacts with the air, right? The metal oxide reacts with the chemical compounds in the air, and depending on the kind of sensor, it will react with maybe with NO2, with CO, you name it, and it's literally an oxidation reduction kind of thing that's happening, which means that some electrons will be either attracted to the piece of metal or being torn away, and as a result, the piece of metal, its resistance change, which means that it's something that can be measured in software, or at least can be measured the microcontroller can measure this change in resistance, which means that if we are to look at a gas concentration of 10 parts per million of VOCs, and this would be something that the data sheet of the sensor would tell me, maybe it will register as 100 ohm, right? If I try and read its resistance. If I'm looking at much more in terms of VOC concentration, well, the resistance will go up, right? And that's something that we can measure. So we have a way to measure, and as often as we like, pretty much, like the sensor is really fast, right? And can pick up variation and changes in gas concentration pretty fast. So as often as we'd like, we can measure the concentration of VOCs, but also the three others compounds that the sensor is able to measure, right? And so that's exactly what I did. And this is where, not knowing anything about AI, I started by using my intuition, right? And it's quite funny because the fact, I ended up talking to some neuroscientists, and they were like, "Yeah, I mean, you're kind of right. That's how our brain works." The idea was that I thought that if I were to capture and to look at just a few seconds of measurements from my different gas sensors, I would be able to capture the concentration of the different compounds, but also it's like on purpose. I didn't want to just like sample the gas concentration once and be like, okay, I have 100 ppms of nitrogen dioxide, 200 ppms of carbon monoxide, blah, blah, blah. I mean, same for ethyl alcohol and VOCs. What is it that I'm smelling? I'm no chemist. I don't know much about how a nose actually works, but I was kind of confident that just sampling one particular data point for each gas wouldn't take me very far, because the concentration changes, right? I don't know, if I am to smell vodka and whiskey, chances are they both pretty much max out the ethyl alcohol sensor, because they are really, really strong in terms of alcohol. But it might be then that the variation of the concentration of ethyl alcohol, I mean, not only it is super high, but maybe for whiskey, it varies slightly more than it does for vodka. Or maybe not, I don't know, but at least I was confident that I needed to capture more than just one data point. And so I quickly settled on 1.5 seconds. Could have been 2, but I realized that 1.5 was actually enough to capture enough information and to have also good reaction times. And what this allows, as we can see, at least on the graph, and then we need to work on the math to get further. But what I can see already sort of visually by capturing 1.5 seconds of data, and so every like 10 times per second, I sample data. So 1.5 seconds is 15 samples. There's already some kind of patterns that at least visually I could identify. Like so I'm looking at whiskey. The amount of nitrogen dioxide seems to be growing steadily. The amount of ethyl alcohol as well, although it is kind of fluctuating. Carbon monoxide seems to be oscillating quite a bit, and it's maybe more flat than the others. So again, like I didn't have practical experience with AI, I've never been able to actually implement my own AI models. But this idea of this thing that people were referring to as feature extraction, it started to become more visual and more tangible, because I was like, okay, I have this sort of table of numbers that you see at the bottom, and there is information in there. It's the kind of information that I'm able to see when I visualize the data on a graph, and it's the kind of data that I probably need to extract through some math, so that it it's actually something that the computer can access, right? And so that's exactly what I did. And this is where Edge Impulse was really helpful in guiding me to do that. I went from this raw data essentially, so 4 sensors, 15 samples per sensor, so that's 60 pretty much random numbers, right? Like if I were to try and write a computer program that takes this data and tries to correlate the data to a particular smell, this would be weird, right? Because I mean, it's just like super unstructured data, and yet the information is hidden somewhere in there. So again, using Edge Impulse, I went through different steps to, well, first make sure that the data looks slightly more organized in terms of, hey, you have 4 sensors and 15 samples of data. Well, let's actually look at them that way. It's going to be 15 times 4 readings. And then something else that needs to be done, or so I was told by the Edge Impulse tooling, was to make sure that the whatever input data you have, try and normalize it so that it's something that's between 0 and 1, because that helps with the computation later on. So be it. Let's just divide all my sensor readings by a factor of 1000. And then that was kind of the next step in terms of trying to extract the meaningful information. And then the very, very interesting part where sort of my intuition met the math and the all the literature, I guess, around machine learning, is this idea of running the signal, the sensor data, through a signal processing block, like the DSP, as the digital signal processing. And here, the table you're looking at, the data structure, is my raw data turned into something that is way more usable and way more meaningful. It's effectively the different columns. You're looking at some math and some statistical formulas that we've ran against the raw data, and we've essentially extracted for each compound the average concentration of each gas. Because again, my intuition was telling me that, yes, I mean, at least the smell, it probably starts with how strong on average such or such a gas compound is. But then it's also about trying to capture the minimum, the maximum, the standard deviation, things that will tell me, oh yeah, okay, vodka, it's strong on average, and then it remains really strong, that the average, the minimum, the maximum are all pretty much the same value. The standard deviation is really small. So that's vodka. That's a sample of how vodka would be. And maybe for whiskey, the average would be reasonably the same, but minimum and maximum would have slightly different values, at least different enough that I would be able to extract meaningful information. And then that's essentially like that's the data to train the model, right? You capture sensor data, you turn it into meaningful features, and then you try and solve an equation where you present your machine learning training pipeline with examples of, hey, whenever you're going to see those numbers, this is coffee, and then those numbers, this is whiskey, etc., etc. And then you eventually build this, except that like I wouldn't have known where to start, like for the right-hand side of the neural network model. This was like,
may I
yes,
with a question? So before you get into this, at what you were talking about is how you were kind of cleaning up the data before it goes into the machine learning model.
Yes.
So it sounds like it's something you could have done with Excel or Python or any number of things, but you took the data, you said, here are the samples from the 4 different sensors for each time slot. So you just made essentially neat rows. Then you ran some basic maths on it to get averages, mean, median, and stuff. And that becomes the raw data now that you're feeding into the neural network. Is that a fair understanding?
Yes, that's absolutely correct. And Yes, and then so it's still in some ways pretty opaque to me, this notion of like neurons and neural networks and layers, essentially what you see on the slide right now. But by doing what you just summarized, I finally realized what, like, although I don't necessarily understand all the math behind a neural network, the way I now think of them is what you see here, what I call the input layer. If you count the number of inputs, you'll find, because it's literally how my neural network looks like. You'll count 20 items as the input. Why is that? We have, I mean, I can go back one slide and you will figure out, like, those are the 20 input elements. Like, I turned my 60, and I don't know why I'm air quoting the 60 here, my 60 row sensor readings, 15 times 4 sensors, that was the 60 as readings that I had. I turned them into 5 statistical characteristics for each of the 4 sensors. So 5 times 4, those are 20 parameters to essentially an equation. Like I have a function that takes 20 numbers as an input, and as an output, what you see on the far end and on the right hand side is the number of classes that I want to be able to recognize. And in most of my examples, at least when I do public talks and so on, I use 3 classes, 3 categories of smell: whiskey, coffee, and ambient air. And so training the model is essentially solving an equation that takes as an input the, in my case, 20 characteristics about the gases, their standard deviation of the CO, minimum of ethyl alcohol, etc., and solve the equation so that as an output you have the probability of the input corresponding to coffee, whiskey, or ambient air. So you try and solve the equation by being like, okay, for this input, the expected output should be 100% whiskey, 0% ambient air, 0% coffee, and then you give another input to the training algorithm to be like, okay, this input, it's 100% ambient air, 0% blah, blah, blah. And then you can sort of imagine, it's just an equation, right? And you try and find the parameters that are part of the hidden layers that are essentially the different knobs that you need to adjust so that effectively in a majority of the situations, when presented with new data, the algorithm, the function will give results that are as close as possible to the reality. And maybe like with new data, it's not going to be telling you, oh yes, this is 100% coffee, 0% X and 0% Y. Maybe it's going to be more, okay, we think it's 95% whiskey, and then, but you get the idea, right? So that's, and I would have never be able to do that without, I guess, 2 things. One is Edge Impulse, and like it's not that they want to plug their solution more than needed, but it's really having this kind of visual workflow and the way to visualize my data. It helped me finally realize what things like feature extraction was. And I guess something else that helped me is playing with like physical things, physical sensors, and that was maybe more actionable than pixels, like I was mentioning earlier. So I see a lot of activity in the chat. Ken, if I cannot pay attention to whether those are questions, if there are questions, it might be worth interrupting me.
Yeah, I'll let you know when they're worth
interrupting.
Jen is actually answering some questions for other people.
Yeah, that's what I thought.
I have your
That's
attention.
awesome.
It's kind of relating what you just said back to what Jen was doing, you're feeding in known samples of different odors, the whiskey, the vodka, the coffee, which are equivalent to the pictures, the labeled pictures that Jen was showing about to her model. And Maurice, if you're still here, it answers the question of can you feed other kinds of data in? So Lobe was very photo oriented, but in this case, you could really feed it anything that you could put into numbers. So my question is, what this 1.5 seconds of raw sensor data, was that, did you have that per kind of odor, or is that all the odors combined? And was that all the training data you provided? Or was
that's a really, really interesting question. Yeah. So for guessing what a smell is, or for what I sometimes refer to as capturing the olfactory fingerprint, you effectively just need a window of 15 samples. But for training, the way I essentially did it is I put the gas sensor on top of the smelly thing for as long as, 2 minutes, 5 minutes, and I capture all that data, right? So if I capture the data at, let's try and do the math together. So I capture the data at 10 hertz, 10 times per second. So I would typically run a recording, a sampling of the data for 2 minutes. So that's 120 seconds. So I effectively get 1,200 readings, right? And so those 1,200 readings, effectively, you have a shit ton of 15 of samples and windows of 15 readings, right? And so all those windows starting at 0 second and ending at 1.5, that's one window that I can feed into the training algorithm. And then starting at 0.1, ending at 1.6, that's another sample that I can take into the model, et cetera, right? And so effectively by recording 2 minutes worth of sensor data, I have a couple hundreds, I guess, of samples of conditions that I can give to the training algorithm to be like, okay, this is whiskey, this is whiskey, this is also whiskey, this is also whiskey, this is also whiskey. But of course, it will also all have some variations, but this is all corresponding to whiskey, and this is all corresponding to what later on. This is,
okay, that makes sense. Yeah, I get it now. So you're capturing chunks of call it 1.5 seconds over and over again for each of the different odors.
Actually, you know what? I'm going to try and real quick just open up my Edge Impulse environment. You know what? It will be even more visual if I show you the. So I apologize if I dive directly into the actual place where I would have my training data. But let's see. I'm trying to find a slightly longer. Yeah, there we go. So those are in the list here. Those are all the samples that I recorded. Different kinds of coffee. Actually, sometimes it would be actual coffee powder. Sometimes it's an actual cup of coffee. But for that one, it is let's say, how long is that one? It's probably a few minutes worth of data. But here I can easily, in the tool, look at only the slice, only the 1.5 second window, and you should. Whatever I went through just before, you should actually see it here, right? If I look at this particular window, those are the 60 samples in completely flat form, but then this is how they are being turned into extracted features, right? And that way I can, I can visually see things like, oh, let's see, do we have a sample of, I want to find something that changes slightly more. Yeah, this one maybe, see, that was me recording intentionally recording a sample where I was slowly approaching the sensor towards the whiskey, towards the bottle of whiskey, so that I would capture this particular condition and this particular situation where the smell would intensify, because I want the model to know that this can happen, like this can be a situation that happens. And if in the future the model sees that pattern, then it's likely whiskey, right? How fast is the concentration of ethyl alcohol increasing? Things like that. This is effectively captured by the model, and I could check that, right? So yeah, I hope that complements my answer to the question.
Yeah. And in fact, I'm really glad you put that up, because that helps me understand the kind of the pre-processing you did. Is that's actually, those are tools built into Edge Impulse. So what you call the CSP block. So I can take it and use that to help kind of clean up the data to feed it into the neural net. So that's all. Those are a bunch of modules within Edge Impulse itself.
Yes. And so I might actually skip the couple next slides, but I will sort of summarize them by staying on that one for a bit. Yes, what you just said is correct. At the end of the day, training the model is, I mean, there's many ways to do it. Training the model is solving the equation, trying to find what are the best parameters so that you can approximate as best as you can all the training data that's being fed into the training algorithm. You try and find what are the parameters for those, what are the values for those parameters in the middle, so that you get the best result. And it's more or less a trial and error process for the machine. And that's why it takes so long. There's ways to take shortcut and try and solve the equation or approximate the equation as fast as possible. It's more or less a random process. And so to your point and to Ken, yes, finding what would be good inputs is something that Edge Impulse can help you do. The fact that you want an average of blah, the min, the max, and things like that. But it might be that my intuition tells me that standard deviation is super important, but maybe it's not. Maybe it's only going to be polluting the equation. It's only going to slow down the process. And so one thing that Edge Impulse, like many other tools now do, is this notion of, if it's going to be a sort of a random process anyways, where we do lots of trial and error, how about we also use this trial and error process to try different combinations of inputs, right? And there's this notion of hyper-parameter tuning, where essentially, like, I might not know in advance what in my data really makes sense. And I think it's average, minimum, and maximum, and standard deviation. But maybe because I suck at math, maybe I don't realize that standard deviation is not really needed if you already have average and minimum and maximum, because maybe the information is already there. And so the tool can, I mean, it takes some potentially some hours of training in the cloud, but it will try different variation. Like, what if we were to try and solve the equation by only using the average? And what if we were to add such and such parameter? What if we were trying to have more hidden layers to capture more information? What would be the result? Do we have better accuracy or not? And so those are all things that the machine learning tools out there, and Azure, like Microsoft Azure, also has something similar in the machine learning studio. Sometimes you might want to use the computer to tell you like if you're not a data scientist, it might make sense actually to go all in that notion of trial and error and trying to optimize your parameters. So and that's pretty impressive actually to see it in action, because you have different variations of the model training in parallel, and you can really quickly identify what works and what doesn't. And maybe you leave the machine in full control, or maybe you're just like run this hyper parameter optimization for just a few minutes, just in terms of helping you figuring out what makes sense and what doesn't. And then you go back to the drawing board and you think some more with your own brain, and then go back to using the machine to optimize them. I mean, it's really fun actually to dive into those things. So
that leads me to a couple of questions that were asked of Jen. First, a simple one. You have an NA result, as Jen did, for something that's not none of the above. It's not coffee or whiskey or vodka. You have to have a category for that.
Yes. Yeah. Let me. That's a really good question. And yeah, so was it Chris earlier? Yeah, Chris asking about what happens when you have outliers kind of stuff. So yes, that's actually super important. Quickly, there's this might be the most technical slide here. Just in a nutshell, what I would summarize that one as: keep in mind these $5 price point that I mentioned earlier. It's almost overkill. Like the kind of neural network, the kind of model that we were looking at just before, it's able to classify a handful of smells with reasonably good accuracy, actually really good accuracy, and it's able to do that in under 1 millisecond. So if you do the math, or if you keep in mind that my algorithm essentially needs to acquire data every 100 milliseconds, then what that means is that what my computer program does is 10 times per second, I spend like a tiny amount of time acquiring data from the sensors, then run the data through the AI model. 1 millisecond later, I have my result, and then I can go back to sleep. Like there's this notion with microcontrollers where you can put them in sleep mode, right, to save energy and so on. And I can do just that, right? I have literally 99% of the time, the device can just be idle and or can do other business, right? It can connect to the internet to send data to the internet, or it can you can manage the graphical user interface maybe. But what that means, like essentially here, is that you don't need a big MCU for things you would think are super advanced, like smelling things. So I guess smelling something is not as advanced as you might think, and you don't need lots of energy either, right? You can do that on a battery powered device with no problem. So to answer and to go back to the point about outliers, question from Chris and from Ken, and almost in the realm of responsible AI. Like, I mean, it's kind of a loaded term, and I don't want to like put too much into it, but I think it's actually important when you look at TinyML and constrained devices, one way or the other, it's called AI, but it's not like it knows everything and it's always going to give accurate results. It's not like there's always trade-offs in terms of how much accuracy the model can achieve and how much of that can fit into your constrained equipment. But the thing is, this equation that we've been trying to solve earlier, it's a function, right? I mean, you feed it with sensor data, it gives you a probability about this data corresponding to smell A, B, or C. Always. That's a function, and that's what it does. And so my model that's able to smell whiskey, coffee, and ambient air, surely I can make it and expose it to the smell of strawberry jam, and it will be like, yeah, that's whiskey. Similarly with honey, right? And so that's a challenge, but it's actually one that's reasonably easy to work around. And my device, I don't know if you remember the video really early on, the demo video of the nose, but effectively the device gives a visual cue, and I think it's something important to have in mind in terms of designing the UI and the UX around all things AI. Yes, the device, if I am to smell honey, it will tell me it's coffee. Like visually, it will tell me it's coffee because it might be coffee after all, if the model thinks it is. But it will also have a wondering emoji face to essentially tell me that it's likely there is an anomaly. And what is an anomaly? It's something that we do as part of the training process of the model. So we capture the model for like smelling, but we also capture a model of what is on average how did the training data look like? Typically, I mean, the kind of information you capture in that model is would be something like, oh yeah, when we did training, on average, the concentration of ethyl alcohol was always between 500 and 1000, no matter what. For ambient air, coffee, and whiskey, it always was. And that means that when later on the nose smells something that is 200 ppms of whatever is the gas that I used in my example, then it will be like, oh yeah, no, I mean, yes, we can put that through the model, but it's very unlikely that you will get accurate results because we've never seen that during training. So we don't know what that is necessarily. So that's something pretty easy to accomplish, right? And pretty important to have. Otherwise, you kind of make the assumption or make the user assume that they are seeing something that's really not the reality. How much time do I have left? Whoever out stuff.
Another 5 minutes. So I'm going to hit you with one more question, which is, in this case, it looks like the training is being done in the cloud somewhere, and then the execution again is on your device.
Yep.
Or not. Then is the training being done on your local machine?
No, the training is happening in the cloud. I haven't explored training on the device. It turns out that for such a model, it's likely possible. For more complex models, for like Jen was saying, for computer vision and like video, etc., it wouldn't even be like possible. But for the model being reasonably small, it could happen on the device, or we could also do the initial training in the cloud. The one training that takes time, the one where you start essentially with virtually like no idea of how to solve the equation, to a point where you've solved the equation for like a particular training set, and then on the device you can do reinforcement learning. So that is, the more the device sees whiskey and the more you confirm to the device that it is indeed whiskey, then it can adapt and adjust the parameters of the function or of the equation without having to start from scratch. And that's something that would be doable and also useful, right? Because you can get better and better accuracy over time. So I want to wrap things up with a few additional thoughts on the fact that I don't know about like all of the folks in the meetup today, but some of you might actually be actual data scientists and know a thing or two about AI. So you might be like, okay, but like you've shown us you're not even using the accurate terms about the math behind AI, and your neural network was pretty dumb and pretty naive. That's kind of the point of the talk to some extent. The fact that when I started, I had no idea where to start. I had no idea about most of the concepts about AI, and literally a couple hours, although I ended up spending more time on it, but in literally a couple hours, I had built an artificial nose. So that's certainly interesting. And I realized that I should maybe go the extra mile. So I ended up teaching myself Blender. And so I designed a 3D enclosure that can be 3D printed, essentially something that is open source as well. Not only is the code of the device open source, but if you have a 3D printer, if you want to build the nose, you can also print the enclosure. And one thing, and this is where it might sound as if I'm just sort of bloating, but I'm not, because I really was the first to be surprised there. But when I had built my device initially, I started to blog about it and to like tweet and share on LinkedIn and so on, and it went viral. And to me, that was kind of awkward, because I mean, I knew that I had built that starting from scratch, not knowing AI, and I had built it in literally a couple hours. And I was like, how come this influencer on LinkedIn shares the post and it reaches like 250,000 people, including folks working in the cosmetics industry or working in the food industry, folks where like I genuinely thought they had solved the problem of building an artificial nose like literally decades ago, except they hadn't. I had folks like senior scientists and chemists from, again, like cosmetics companies and so on, reaching out and being like, I had, in a nutshell, telling me, oh, I had no idea gas sensors for VOCs existed. Like, and I'm not kidding. I'm not even talking about the fact that those sensors, you can have them go through an AI model. I'm just talking about the sensor literally. So I think there's a lesson for all of us tech enthusiasts. Like I breathe sensors and IoT all day, and I mean, I was assuming that at least like most people in the tech industry were familiar with the fact that yes, there are sensors for more than just temperature and humidity, and it turns out that maybe not. So let alone talking AI, etc. Right? I mean, it's there's sometimes, I guess sometimes pet projects can be interesting in that sense, because you work on stuff using like super affordable hardware and not necessarily doing rocket science, and you realize that I mean, it's sort of useful. So it ended up being featured in some magazines and on Mashable.com. So that was really cool. And I realized that I should go further, which I did. And I probably won't have time to show you much about that. But essentially, if you go check out the GitHub repository and all the articles out there, you will find that now the nose is not only a smart nose, but it's a smart connected nose. What I wanted to showcase essentially is use cases where you have a device capable of telling you when you have foul air in the room, right? Restrooms, potentially, it starts smelling bad. You want to send people to clean the facility, right? And moving from a scenario where you send cleaning personnel every morning at 5 a.m., no matter what, to a point where it's COVID and the restrooms are not used as much, maybe. And so you want to send people only when it's actually needed, right? And there's many ways to accomplish that. Maybe you can have a people counter, but a sniffing device could be interesting, right? Because it can also, and that's what apparently some recent articles seem to indicate. Maybe you not only smell when it smells bad, but you also smell when it smells like COVID, because it turns out it would seem that there are sensors that can smell COVID. So, which is interesting and goes back to this discussion before of reinforcement learning. When you have a device that's effectively like sitting there, but is capable of connecting to the internet, at day one, the device might be programmed and using a basic AI model that can tell clean air apart from bad air. But then 6 months down the road, there's this super new development in the sensor industry where people figure out how to train a model to recognize COVID, and then over the air, with no human intervention whatsoever, you deploy a new version of the model where you can smell, when you can smell more things, right? And so this connected device end up participating to Internet of Things scenarios, right? And so the nose can report over the air and as often or as little as you want it to, can send data to the cloud, right? It can report the raw sensor readings, it can report what it is smelling, and the other way around, from the cloud, you can deploy new models, right? And so I ended up connecting the device to Azure IoT Central, which is our IoT cloud offering. And so in real time, if I were someone operating a fleet of like buildings and restrooms and whatnot, like I could have some nice dashboards letting me know where and when something smells bad, kind of stuff. So yeah, that's the idea, and I think I need to wrap things up. So I will go quickly to the I have one. So are we at time? Or do we have a hard stop? Or
go ahead. As long as people are sticking around, we can stick around as well.
Okay. So just let me try and quickly go slightly further from moving from here to sort of the next step. Here, the idea is to sort of think of TinyML as being one of those potential contributors to what I would call not necessarily the Internet of Things, but more the Internet of Signals. You have devices out there, things that let you know about what's happening, right? And it can be sensor data, it can be, it smells bad kind of signal, right? And so that particular signal, it starts making a lot of sense when you, and this is what some people refer to as digital twins as well, this idea of, okay, I'm in the business of selling a service where I go and clean office buildings and restrooms and whatnot. I've been in this industry and in this business for decades. So I know my stuff. Like I already have a database or like an ERP or you name it, where I've modeled my my fleet of all my customers, like all the buildings that I manage, who are the people responsible for such and such part of the building. I have maybe some cleaning schedules as well. They might be like super dynamic, right? People take some time off, people call in sick. It's highly dynamic. And so this information model I have, like it's part of my information system. But what if I can start adding and complementing my my information model with physical, like with the representation of physical devices, right? And I have a technician that just contacted Benjamin or whoever and just bought an artificial nose, and they went and deployed and provisioned the nose in the ceiling of the restrooms that are in floor number 3 of building X in city Y, right? And so we have this information in our model, in our database, if you will. And so now next thing that happens is that particular device sending a signal. And so that's interesting because it's not only a signal, it's a signal that you can correlate with a lot of things, right? And with like you have context essentially. And so, yeah, that particular nose just told me it smells like foul air. So it's not only about the nose potentially sending a local beep in the field that only takes you so far, right? I mean, it can beep as much as it wants if no one is there to clean or to take action and to know what taking an action even means, then it's not that useful. Whereas if you send the data to the cloud, then you can start correlating the data to, oh, okay, the nose is in this particular building, was responsible for cleaning this building. Oh, it's John. oh wait, no, my Outlook, like if I look in Outlook, it looks like John is out of office today. So what's the backup, right? And let's send a text to that person so that they take action. So that's the kind of scenario. And I actually even have a quick demo kind of related, just maybe a slightly different use case. You want to build a solution for monitoring when people in retirement homes, monitoring, I guess, to some extent, their mental health and whether they're doing good or not. So I have, like, I'm monitoring a fleet of, let's see, like I want to have a sort of a snapshot of whether the person in their apartment is happy. And so did they get their coffee today? Because if not, then it might be a sign that they are, I mean, they are not feeling so well. So the way it would work, hello, that was just for checking that everyone is looking at the camera. My nice kitty. Sorry. Yeah, so I have my artificial nose on my desk. Actually, it is. I mean, it's not attached to the enclosure, but right now the nose is smelling ambient air, and it's sending data to the cloud, right? So let me just make sure that I have my IP camera turned on, because I might, yeah, use it later on. So yeah, right now I'm smelling ambient air, and I have a model. Let me just make sure that I start from scratch. So we are looking at like the kind of graph that we were looking at earlier with the city of Chicago, etc. Like this would be a similar graph in Azure Digital Twins, but this time for the nursing home. And the nursing home it's a particular building, and it has a couple rooms, right? And so not much happens if we just look at it that way. But what's happening though is that there is in the system, there is a sensor that is sending data every seconds or so, and that is my artificial nose. So if I refresh the graph, there is actually a nose in the system. There is a device that has a twin, I guess, and it's sending data. Like if we look here on the right-hand side, it says, where is it? Yeah, I need to make sure that it actually smells something different. Oh yeah, no, sorry, it's here, ambient 96%. So the nose right now is smelling ambient air at 96%. And if I just, where is my camera? It's here. So if I switch to my IP camera, sorry, I need to just, yeah, sec. Sorry about that. There we go. Okay, that's not what I want to show. There we go. Okay, so we have the nose right here. It's still smelling ambient air. And right here we have, so we have the room, and I'm going to run, I'm essentially using, so it's Blender. The tool that I'm using is Blender, and it's now I've scripted my 3D model of the nursing home so that every 5 seconds or so, every 2 seconds actually, I query the Azure Digital Twins graph to see if there's interesting information for me to show and to display. And right now, it doesn't look like there is, but there will be as soon as here I indicate in the system that, hey, you know what? The kitchen, the nose is in the kitchen, right? Like this kind of, I need to show you something first. Okay, sorry about that. Okay, so now the nose is in the kitchen, which means that we've established this correlation between the digital twin of the nose and the digital twin of the kitchen, which means that whenever we want, really, we can query the system to ask the system, hey, what is it smelling? What is it smelling like in the kitchen, sort of? And so right now, so the nose is telling me that it's smelling like ambient air. And if I go here, oh yeah, it is indeed. So sorry about that. It is indeed smelling like ambient air, right? And we could all, of course, think about all sorts of smart visualizations. It might not even make sense to have a 3D model of the nursing home. But let me try and show you what happens now if, and you're still looking at my webcam here, if I put the sensor in the kind of coffee that I have here. So now,
with that kitten.
Yes, but I won. And let's see. So if you look at my webcam, you should see. So you see the sensor readings on the graph. They start going up, and now it should start thinking it's coffee.
Oh thinking it's a kitten.
Yeah, I didn't train the model against kitten. There we go. So it smells like coffee. And let's see about the 3D model. Oh yeah, now we have the visual feedback as well, right? So, oh, it's going to end really bad because that's coffee powder in there. So that was for the demo.
You're going to have a caffeinated kitten there pretty quick. This is great. Thank you. I think we are.
Yeah, we're at time. So some links that I can maybe put in the chat as well. Yeah, there's a GitHub repo with all the code. Feel free to check that one out. It has the 3D model and everything. There's a great video that my colleagues at Microsoft AI helped put together, which you might find interesting as well. And yeah, that's thanks for the additional 10 minutes or so, and for sticking around. That was great.
Thank you. This is great. I really like seeing this stuff in action and seeing kind of how you input the stuff into Edge Impulse, because that kind of gives me more of a feeling of where to start. Like you got to start somewhere, and that's that really helps. So, and you've become famous as the artificial nose guy.
Which is, yeah, that was an interesting development.
Who knew, right? Who knew? Anyway, thank you all for sticking around. And I'll get the recording up in the next few days if anyone wants to revisit this. And that was great. Both of Jen's gone, but thank you.
Thank you. I appreciate it very much.
Yeah.
Excellent.
Yeah, Christopher, say hi, and yeah, we should chat sometime, catch up.
Yeah, man, I'll shoot you an email or something.
Yeah.
All right. Take care,
All right,
guys.
guys.
Go to run.
All right.
Bye-bye.
Thank you all very much.
Thank you so much,
Take care.
Benjamin.
Right. Bye-bye.
Thank you.
Thank you,
Bye.
Benjamin.